Hey guys, thanks for joining me this morning. Just going to be doing some final exam review problems. I so this let's see here. So some people have finals on Friday, some people have finals next week. So whenever you're watching this, I hope it's helpful. Um, what I plan on doing is just taking some requests from people. I have the chat room open, and I'm just going to check it out. So if you're watching this live, go ahead and go to the chat room in the description for the video. Just there's a link there. Click on that. And so far, I got one question. Excuse me. So far, I got one question, and we're going to go ahead and look at that first. All right. And if you have any other questions, just go ahead and let me know. Alrighty. So here we are. So let me go ahead and bring up the screen. The first question I got was, I got a request to do a square loop of wire for Ampere's principle. Using Ampere's principle, find the magnetic field at the center of the wire. And so this is on page 213 of the textbook. This is going to be exercise 5. All right. So let's start off with this, and you can leave any questions you have in the chat room while I'm working on this. All right. So let's go ahead and bring it up. Okay. So let's go ahead and draw that out. So this is just a finite wire problem, and really finding the magnetic field due to it. So we got some finite piece of wire formed into a square, and it has a current around it, I. And the question is to find the magnetic field at the center of the square if each length of the square is L. Okay. So I'm just going to make sure everything's showing up on the screen, okay? Yeah, it is. Good. All right, so let's continue here. Alrighty, so the law you want to use to solve this, to find the magnetic field right at the center, is going to be Biot-Savart, or Ampere's principle. That gives you a little magnetic field contribution dB due to a little piece of wire ds. All right. We have mu naught I over 4 pi ds cross r over r cubed, where r is a vector that points from the ds element to the point where we're calculating the magnetic field dB. All right, so r is going to be this. All right, and this is our little ds vector here. All right. Alrighty, now because this problem is made up of 4 pieces of wire, all right, what we're essentially going to do is go ahead and split it up into 4 little sections. All right, so we're going to have a section here with a current I, and here is the part where we're calculating the magnetic field at a distance L over 2 away, L over 2. Perpendicular distance. Alright, and let's draw our ds vector here. ds. Alright, going this way, and our r vector is going up. Alrighty, this is r. Okay, and so what we're going to do is just write Ampere's principle for this piece of wire, where B total is going to be 4 times the sum of dB over one wire. One wire. Okay. So I've broken this up into 4 parts. 1, 2, 3, 4 wires. Right, but they're all going to give the same contribution. Alrighty then. Alright, so let's go ahead and figure this all out. So here's the law. I'm just going to go ahead and copy and paste this down here and plug in what each vector is to the best of my knowledge. Alrighty, there we are. Alright, so ds, well, what I can do is define a coordinate system. I can set, let's go ahead and use blue here. I'm going to set the x-axis equal to 0 here, and then we'll be positive x this way. This will be at a location x. Alrighty. Good, good. And so now I have ds is essentially equal to dx ix. Alrighty. our r vector now is going to have two components, an x and a y component. Now in this cross product, the only component that matters is that y component. The x components in the cross product won't have any effect. All right. Getting a lot of, sorry. Okay, so this is equal to mu I over 4 pi. And now what we want is essentially the y component of this vector, so let's call our y direction up. All right. So the y component here, we can write in terms of an angle, right? So we can write it in terms of this angle if we want, in terms of this angle. We're going to try this angle first. All right. Good. So, and it turns out that this distance here is just going to be L over 2 anyway. Okay, so that R cosine theta is L over 2. So we have R being equal to, it's going to be R sine theta Ix plus, and then R cosine theta, which is always going to be L over 2 Iy. All right. And so the cross product of those two are going to give us L over 2, where are we? Sorry, L over 2, and then we're going to get dx here, dx divided by r cubed. And so r cubed is going to be the square root, looks like here, r cubed is going to be related to what we're writing here. For now, let's just write it like that, and then we'll figure it out in terms of x. All right. Okay. So once again, if you have any questions, just let me know. But we do have to integrate to be honest, right? To integrate over the wire here. So this is going to be an integral from x equal to 0 to x equal to the length of the wire, which is going to be L. All right, L. All right. So looks a bit messy, but there we go. Okay. Let's go ahead and move this out of the way. Alrighty. Okay. All right. And so on a, oh, forgot my bound. So on a test, you're not expected to do this here, this integral, but you can, these integrals will be given to you at the front of the test, if they are given. The challenge here is just to get this all in terms of x, right? And so that's what you want to do. So my coordinate system isn't really accommodating for this. It's probably better to, instead of calling this 0, we're going to call 0 let's say right here at the center, x equal to 0 at the center. So this is negative L over 2 here, and then this is L over 2 over here. All right, L over 2. So the length of this is L over 2 over here. And then what we're gonna do, hey, I'm just doing a review video on YouTube real quick. Yeah. So sorry about the
Yeah.
Okay. So we're going to integrate here. So now that this is going to become this little length here, is going to call it x. And so on this triangle, what we're going to have is a length of negative x here, this being a length r, right? Because on triangles, we want to have positive values, okay? And since x is less than 0 to the left of the origin, let's put negative x on this triangle, okay? And this is going to be L over 2. So now we're going to integrate from negative L over 2 to L over 2. Alrighty. And since it's since we essentially have the same integral on either side of this origin here, we can just double the integral from negative L over 2 to 0. So let's take 2 times the integral from negative L over 2 to 0. Alrighty. And R here is just given by this figure. R is going to be x squared plus L over 2 squared. Sorry. L over 2 squared, and then all to the 1/2, but then cubed, so it's to the 3 halves. And what's the overall direction of ds cross r? Well, ds cross r, according to this picture, if you use the right-hand rule, is going to point out. So this is going to be outward. Alrighty. And so, yeah, this is what I was saying. These sorts of integrals would be given at the front of the test if you were expected to evaluate them, but in this case, no. And let's not forget our overall factor of 4, right? That's outside here, 4. And so we need that factor here and that factor up here as well. So 4 times 2 gives us 8. Or we could just cancel the 4 below, either way. Alrighty. So that would be the total magnetic field. This integral, if you had to do it explicitly, you would want to do sort of a trig substitution and integrate over this angle here. Alright? And once you set up the integral so it's integrated over that angle, you end up getting a pretty easy integral. Alright. So there we are. Alrighty. And so that's all that was asked so far. If you have any questions on that, let me know. And also, if you have any other questions on anything else, let me know. Just let me know in the chat room. That's the best place for me to find it. Alright. Okay. So we have nothing right now. So while you guys are coming up with another question, let's look at something else. Let's go to Safari here. And let's see here. Alrighty. See if we can find a good question to go over. And the circuit below switch. This might be a good one. Yeah, this might do it. Okay, so let's take a look at this one. In a circuit below, the switch has been closed for a long time, so the steady state has been reached. Find the current through the resistor and the charges on the capacitors. All right. Okay. So let's see if I can remember this one. Let me go ahead and bring it up on my other computer real quick so I can write that down. 2012. Okay. And it is number 3. Okay, 2012 number 3. Let's take a look at that. Alrighty. Okay. So what do we got? Got a battery here. Okay. And we have capacitor C1, inductor, switch, resistor, so R, and then C2 over here. Okay. And what are we asked for? We are asked, in the circuit below, it's been closed for a long time, find the current through the resistor and the charges on the capacitors. All right. So let's say the switch has been closed for a long time. All right. What are the charges on each of these capacitors? What is the current through the resistor? All right. So what you want to do is you want to go ahead and you want to label each charge. So let's call this Q1 positive, Q2 or Q1 minus here. And let's go ahead and call this also positive Q2 and then negative Q2. So your answers, as I've said a few times, will depend on how you label your charges. And let's say the current's going to go this way. So let me label that in another color. Let's say green. Let's say the current is going to go this way in this wire. And that's it. Now let's think about this a little more carefully. All right. Now whenever this has reached the steady state, we can say that all currents going in and out of capacitors is 0, So I is equal to 0 in and out of C's, or capacitors. All right. And then di of that means there's going to be no, I'm going to go and highlight where we know for sure there's no current and see what we can say about it. It's going to be no current here, no current here, right? There's going to be no current here, no current here. So let's go ahead and fill in the blanks. There's definitely no current here, definitely no current here. If there's no current going in or out of this wire, there can't be any current going through this wire. All right? And that means going, so there's no current in any of these places, so there's no current flowing into here, and no current flowing ultimately up here either, right? So that's the argument. So essentially I is equal to 0 everywhere here. All right, in the steady state. So I is equal to 0. Good. Does that mean we can't write anything else? No, we still have a law that applies, and our law is going to be Faraday's law, the integral v dot dr is equal to negative d dt of flux. Alrighty. Goody goody. Alright, and I am getting some requests. Number 7 on 2009. I appreciate that. I appreciate that. Somebody's saying, oh, okay, that nothing is showing up on the screen. Thank you. Alright. So let me go ahead and bring that up. Sorry about that. Not sure why that happened. Okay, let's go ahead and go back through this. So here's the circuit I have. All right, let me get rid of this part and this part. This part. Okay. And so the main idea is, while I'm erasing this, in the steady state, all the currents are 0, and all of the time derivatives of current are also 0, unless you have an LC circuit. All right. And so there's no, we know for sure there's no, so all the currents rather going in and out of capacitors are 0, not all currents in general, right? So these currents are definitely 0, and these currents and these wires are definitely 0. Okay. There we are. And that means there can be no current going through this wire. If there's no current coming into this wire, there's no current through it, and the whole way around, absolutely no current in the steady state. Okay. And thanks 855 for and 932 for pointing that out. All right, the screen wasn't working. So because this is equal to negative d dt plus or minus Li for this little inductor here, I assume that L is going to include self-inductance. Let me just go ahead and look at that real quick on this problem. Yeah, L is going to include self-inductance, so we can write it like that. All right. And so di dt is going to be 0 in the steady state, so this term is going to be 0. So the integral v dot dr around either of these loops is going to be 0. So let's do both. So the first loop, let's call this the first loop. Let's go around this way. Let's call this the second loop. Let's go around this way. Each of these are going to have a ds vector pointing out and out, which we won't need here. All right. And so the first loop we are going to have. All right, let's start here. Going over the capacitor, the field's pointing to the right, and we're integrating to the left, so we're going to get negative Q1C over C1. And then we're going to get plus V is equal to 0. And for loop 2, let's start here and go around. We're just going to get negative Q2 over C2 is equal to 0. This equation tells me that Q2 is equal to 0. And this equation tells me that Q1 is equal to C1V. All right. And so these are the steady state values of everything. That, and that. Okay. Alrighty, and part B of this problem says, let's say the switch is opened again. So let's write B, and then now open switch. Okay. So let's say we have this initial charge on this capacitor, okay, and then we go up here and we open this switch. All right. So the switch is now opened again, and we want to find the charge on the capacitor C2 as a function of time. Alrighty. The steady state current, the charge, and the charge. Sorry about that, guys. I have no idea what happened. And then let's open the switch. All right. So let's open the switch. I have the wrong screen showing. Okay, I think I fixed it. Let me know if it's good now. Screen isn't showing. Somebody let me know if this is up now. Let me go ahead and type in the chat. Sorry about this. Is screen up now? Let's see. Okay, it's good. All right. So let's keep on going. So now we open up the switch, and here we are. We're gonna open that up, and so when we open that up, we're gonna have an initial charge here. All right. So let's go ahead and erase all this greenness. This greenness needs to go so we can see what's going on. Alrighty. All right. Alright, so we have an initial charge here. Alright, so that's going to cause some current to flow. It's going to, let's see here, we are then going to have some initial current in here. Alright, but we cannot integrate E dot dr. Alright, so I think I'm just going to get everything being 0, which is not good. Is that going to be right? That doesn't look very savory. Let me check this. Let me look this up. Let's see here. Sorry, guys. Previous tests. Oh, and that screen went down. Okay. Let's put it back up. 2012. Okay. So I'm just checking to see. I think everything's gonna end up being 0 the way I have it worked out. Yeah. Yeah, I got. So this is true. I just looked up the solution. Everything's gonna end up being 0. All right. Or Q2 as a function of time, rather, is going to be 0. So part A was totally right. In part B, you open this switch, okay? So unfortunately, we have an initial charge of Q2 being 0 and an initial current in this wire being 0 because there was no current in the steady state, okay? If there's no initial charge, there's no initial current, nothing's going to happen. And let's go ahead and prove that, okay? So the way we do that is by integrating around 2. Okay, so let's integrate around 2. Here we are. Okay. And let's just go ahead and pull down that diagram so I can see what I'm integrating around. All right. Kind of paranoid the screen's going to go down or something's going to break. Okay, so let's integrate around loop 2 here. All right, let's go ahead and start here and go around. So the first term we're going to get is negative Q2 over, negative Q2 over C2. And so the law we're using is the integral v dot dr around the loop, which is what we just did for loop 2, is negative d dt, and then plus or minus li plus minus li. Okay, so this is equal to negative d dt. And now because I have positive ds pointing out, remember that L is given by the flux ds is pointing out, be induced due to this current, well, supposed current flow, so we need a supposed direction of current. Let's suppose the current's going to flow that way, okay? Then B is going, yes, B induced is going to be out, ds is going to be out, and so here we're going to just get a positive Li, okay? And what you can do is solve this differential equation, knowing that in this case, we're going to have I is equal to negative dq2 over dt. So we're going to get negative q2 over c2 is equal to, and then we have two derivatives here. We have a d dt here, d dt here. So we get d2 q2 over dt twice, like that. All right. We get no. There we are. We can solve this differential equation. The solution is going to look something like this. Q2 is equal to k cosine omega t plus b sine omega t. And the problem we have is that we have these initial conditions.